Okay, so we're working through some examples. So here's our first one. We want to use differentials to approximate the increase in the area of a soap bubble when its radius increases from 3 to 3.025 inches. And just for fun, we'll also compare that to the actual change in area. Good. So I would give you this on the exam as well. The surface area of a sphere is 4 pi r squared. Right, so then we could say that dA over dr is equal to 8 pi r. You could rewrite that in terms of our differentials by saying that dA is 8 pi r times dr. Good, now we just have to plug in our numbers. So dA is going to be 8 pi. The r you're going to use is the initial r. So always use the initial r, the simple r. And then the change in r is going to be 0.25 inches, right? Oops, 0.025. Good. And then we just compute that on our calculator. This is why I was mentioning in the previous video there that you probably would it would be a good idea to have a calculator just to make little computations like this. So in this case we get 0.6 pi or 1.88 square inches. So you could say square inches that way. Good. Now the actual change in the area, right, is going to be the area at the new value, 3.025, minus the area using the old radius. So I'm thinking of area as a function now, right? And so that's going to be 4 pi times 3.025 squared minus 4 pi times 3 squared. Good. And so notice you could just factor out the 4 pi. And so then we get 3.025 squared minus 3 squared. Good. And so if we compute that on the calculator, let's see, we get 1.8928. Okay, so you see that that is very close, right? Good. So that is a good approximation. All right, let's continue with this, the approximations, and let's do something similar. I'll pause the video while I write down the questions so you don't have to watch me write it. Good. So it looks like we've got a function y equals 1 over x equals 1, and dx is 1/2. Find delta y and dy numerically and on a graph. And I should note right away that we always assume, right, that dx, excuse me, shouldn't have that cup of coffee. Dx is equal to delta x. Okay, so our delta x here is 1/2, which is equal to dx. Our delta y is f of x plus delta x, which would be 3/2, minus our f of y, f of x, which is f of 1. Good, so that's looks like 2/3 minus 1, huh? Minus 1/3. So that means as you go from 1 to 3/2, the function drops by 1/3, right? Good. And so what is our dy? Our dy is f prime of x dx. And it looks like f prime of x is minus x to the minus 2 power, or you could write it as minus 1 over x squared times dx. And now we're evaluating that at x equals 1 and dx equals 1/2. Good. And so let's see, that's going to be minus 1/2, I guess, huh? Good. All right. Now if, let's go ahead and draw a picture of what's happening here. So 1 over x looks like this, right? So at x equals 1, we have a function like that, and let's see if I can draw this in a decent way. Well, close enough. Okay, maybe I'll make this 1, not to scale. Oops. So that's 1, 1. and then this will be my 1/2, or 3/2, right? Okay. 3/2, good. Okay, so then, yeah, so if we drop down to 3/2 here, right, the change in the function is going from 1 to 2/3, right? And so this was our delta y is minus 1/3, and then the change to the change all the way down, maybe I'll use a different color. The change all the way down to the tangent line is the dy, right? It's minus 1/2. Good. So we're starting at the 1 and then we're dropping to either, we're dropping by negative 1/3 or negative 1/2. Very good. All right. So let me pause here and we'll get another question up. Okay, so this time I've got a function f of x equals 1/3 x cubed minus x plus c. And I want to show that this has at most 3 real roots. And so just a couple of notes about the question. Roots means the zeros of the function. That's where the function crosses the x-intercept, or x-axis. And at most would mean that you may have no real roots, or no real zeros. You might have 2 real zeros, or you might have no solution. Okay? So, let's see, why would this have at most 3 real roots? Well, let's take a look at the derivative. So if we take a look at f prime of x, I see that's going to be x squared minus 1. And so if I set that equal to 0, I see that x is equal to plus or minus 1. And so therefore f prime of x equals 0 at 2 points. Good. Now, suppose that f of x has 4 real roots. Okay. Or maybe we will work on the 3 first. 3 real roots first. Okay, so that means that f of x is equal to 0 at 3 places. Right, so let's just call these x1, x2, and x3. The question is this possible, what you're looking at right here? Well, the idea here is that f of x can cross the x-axis here. Notice that if the x-axis, let me say that again, if f of x crosses the x-axis here and here, that would mean that the derivative has to be 0 somewhere in between, right? And similarly here, the derivative would have to be 0 somewhere in between. And so is it possible for this function, f of x, to have a derivative that is equal to 0 at 2 places? And we've just shown that it is. So therefore, f of x could have 3 real solutions. Now, think about the 2 real solutions. Could f of x just have 2 real solutions, x1 and x2? Or real roots, sorry. This is also possible, right? Because our Rolle's theorem says that the derivative equals 0 at 1 point on the graph somewhere. Okay, we know that f prime of x is equal to 0 at 2 points, so it is possible for this to happen, right? Good. All right. And then finally, is it possible that the function just has 1? Sure, that's possible. Can we draw a picture of one that does that? And that's still equal to 0 here and here? Let's see if we can do that. So I know my derivative is 0 here, so I'm drawing little horizontal lines there. And also at some point, the function goes through the x-axis. So what kind of but only 1 point. Right, so can we draw a picture of a function that does that? How about if the origin, let's just make the function cross the x-axis at the origin. How about this function? And then we'll just have it kind of pop up here, and then it doesn't have to cross down again. We can just make it go like that. And then down here, we could do this same kind of a mirror image, right? So that would be an example where the function, where our derivative is still 0 there, and we only cross at one point. And then of course, if you just shift this graph up so that you don't have any crossings at all, right, then f of x doesn't have any crossings. Good. Now, the last question is can you have more than 3? Can f of x cross the x-axis more than 3 times? For example, 4 times. It cannot, right? By the same argument, 1, 2, 3, 4. If it crosses at 4 points, what has to be true? Between each of those crossings, right, the derivative has to be equal to 0 somewhere. Somewhere in here, the derivative has to be equal to 0. And so the derivative would have to be 0 how many times? 3 times. The derivative would have to be 0 at some x in this interval and at some x in that interval. Therefore, that cannot happen, right? Why? Because the derivative is only 0 at 2 points. Okay, so what's the summary of our answer here? Because f prime of x equals 0 at exactly 2 points, f of x equals 0 can occur at most 3 times. Good, so this would be the summary of how you would answer that. Good, so I'm going to pause here and we'll start up with a new video with some more exercises.